Well, tonight we want to talk about, again, this is the second series on the revolution and coming revolution in fundamental physics. And we last time talked about David Gross's talk, and I think, Mike, you thought maybe he was here, and I don't know how I gave you that impression, but I got an email from Mike says, well, I sure would like to hear David's next talk. And so I had to kind of help him understand. I wish we could have somebody. Someday we're going to have those luminaries here, and that would be great. But right now we were just talking about his talk. And he had given this talk all over the country, and it's on the internet, and you can get it. But so this is the second one, and I recently called it, Where in the World is Susie? Does anybody know what Susie is? Yeah, supersymmetry, and of course the LHC's coming, and so, but I thought, well, maybe not very many understood what supersymmetry is, or I was with an actual physicist. He's retired, but he taught at the university up here, and I was telling him about it, and I said, well, you've got the LHC coming on, and he says, remind me again what the LHC is. So I decided I probably better change this a little bit, and so I did. So I'm calling it What Are We, Where Did We Come From, and Where Are We Going? Now, we talked a little bit about the crisis and the paradoxes in fundamental physics. And this young guy here, Arkani Hamed, says he's an upcoming physicist that has done some great work. And he says, many of us feel that our current struggles are paving the way for a revolution in our understanding, and it's the same kind of revolution that we saw in the early 20th century. And it is, it's just really an exciting time to be around. I mean, dark energy, dark matter, this idea of supersymmetry, the Higgs particle, and then all the extra dimensions with brains, D brains, P brains, D brains, warp brains. It's really amazing, and it's moving fast. And so they've got some real problems that, because what's happened, of course, our technology advanced with what we had learned in fundamental physics, and then that enabled us to increase our powers of observation, and so then we find out we don't know as much as we thought we did, and so on. So it's a pretty good time to be around. Now, the original program of Newton's, he started a program of research, really. The dictum for that program was interpreted to be focus on the forces. That's what they focused on, and they used the calculus, and they were do what they wanted to do, with the goal of reducing the description of nature to a few kinds of interactions among a few elementary particles, So they've pursued that with vigor for 200-300 years, and it's come about. Now, we were talking about, remember you and I, Larry, were talking about in priesthood meeting about Hoyle. Yeah, you had some real strong opinions about that guy, but he for a long time withstood this idea of the Big Bang and insisted that the universe wasn't expanding. There still are people who insist on that. There are some people who will seriously defend the fact that the Earth is not round too. But there are a lot of people who will not buy the expanding universe, and thus this Big Bang, hot Big Bang. And they measured pretty much, so our understanding, our current view of this thing is that 14 billion years ago there was this Big Bang. Before the bang, there was an infinitely small, infinitely dense, infinitely hot, infinitely energetic, whatever, primordial universe that burst. Now they're thinking maybe it was some brains that came together and collided, but at any rate, there was this inflation thing, and then several different epochs that happened, and the equations, as we talked about last time, break down at the beginning. So it's really not very satisfactory in that sense. But if they can get by that, then they can say, well, you know, at 1/100,000th of a second, quarks and electrons and radiation and whatnot, and the gluons, you know, we're all in there in a mix. And then a couple 100,000 years later, you know, everything is solidified into the constituents of atoms, and then, of course, congealed into atoms and galaxies and stars and all that kind of stuff. So that's where we're at. And they were out to figure out how this all happened, because they, you know, before wasn't too many years ago, we didn't have spacecraft and so on to measure things, but we did have this. So the standard model of particles. So it all kind of once we did have spacecraft, this science here had become good enough to actually use in that scenario of the Big Bang. So they came up with what they call Big Bang nucleosynthesis, and determine how these particles came about. But the way they figured out the standard model, what they call the standard model of particle physics, was that there's three families, these three rows here, with quarks and leptons, and the three leptons are the electron and the muon and the tau particle with their neutrinos. You probably can't read that. It gets pretty blurry there. And then each one of those families has its own pair of quarks, an up and down quark for the normal stable matter, and then charmed and strange quarks, and top and bottom quarks. And then over here are the gluons and photons down on the bottom, and then there's a minus and plus W boson and a Z boson. That all works in a different way. But these interact, these are the particles, and the interactions are actually viewed as particles because they're viewed as exchanging particles. But the problem is that we've got this hierarchy of mass here, this range of mass, 5 orders of magnitude, which they can't explain. And there's a lot of things that they can't explain. Can you read that? It works well because it can make some real good calculations, but it doesn't answer a lot of the questions. And these are the questions, some of the, you know, now they think that neutrinos recently, they discovered, have some small mass, all right? And then the electron, of course, has a little mass, but the proton over here, I don't show the proton, but it would come from the up and down quark masses, the energy that binds them together, and so on. But then you just keep going up, you see, until you get to the top one, the top quark, and look how huge it is compared to the neutrinos. Then you got the big WZ bosons, and so on. So there leaves a lot of questions. Why these different sizes? Why all these different particles? There must be some law that determines this, but they don't know what it is, you see. And then there's 3 questions here. Why are there so many particles? Where does mass come from? And why wasn't all the matter eliminated? You know, why is there more matter than antimatter? If it had been created in equal amounts, it would have annihilated, right? So they don't know why that is. There's a lot of questions that they know. And I've taken this unification, energy unification thing, where the forces are actually unified at this Planck scale that we talked about last time. I actually turned it around to go with the Big Bang thing, because the Big Bang starts from the left and cools off, so I thought, well, let's do it that way too. And so at that Planck scale is where these forces unify according to the gut theories, the grand unification theories. But they don't quite, if you look at this closely, they don't quite come together without this thing called supersymmetry. So that's Susie, and that's what we're going to be looking for. And also, we want to understand this Higgs mass, because it's a Higgs particle. It's supposed to, we'll see more about this later, it's supposed to give the other particles their mass, all right? But they don't know why it's at this level, because with the quantum corrections that they use, the renormalization procedures that they have, that mass should be way up in here, but somehow it's held back, and they don't know why. So there's this whole scale of energy is just perplexing, and the biggest problem is to figure out, because here's the Planck scale, and this is where gravity is unified with the other forces. So why is there such a huge Hi. Hello. How are you? Is this your first time?
Second.
Second, okay. So you got a brochure. I was just trying to make sure everybody gets
Yes.
a brochure. Pass around the thing to him. And, let's see, what's your name?
Mike Breakerhoff.
Oh, Mike. Okay, good, Mike. Like you to, I know you signed up last time. We're trying to get everybody signed up this time too, if you will. So it turns out that these procedures, I can't stay behind this damn thing. I really have a hard time talking and standing still, really. But the film didn't come out. I was all in the dark. If any of you saw what was online, and so they want me to stand in the light, but I can't stay here. Anyway, point is all this worked out with renormalization and this idea of quantum corrections, all right? But then it's the quantum corrections that cause this problem here. If they actually applied the quantum corrections, they would be way up there. But by getting this supersymmetry, each particle having its super partner, then the momentum and everything works out so that it makes sense, but not without supersymmetry. So that's why they're looking for it. So I didn't know this, but I found here just a few weeks ago there was a spread in Scientific American about the coming revolution in particle physics. So I thought, wow, that's really great. And, I wish I could have had copies here, but it's online, a lot of it. And I went to the library and I got a little bit out of it, but they're talking about the same things we're talking about, but they explain a lot about the Higgs particle, especially supersymmetry. And that's in this past February edition. All right, so we're going to look for the Higgs particle. That's the first thing.
When the Large Hadron Collider and its massive detectors become operational in 2007, one of its primary tasks will be to look for the Higgs boson. Although formulated by several theorists, it takes its name from one of its proponents, Professor Peter Higgs of Edinburgh University, who today leads a quiet life in an old area of Edinburgh known as Newtown. As he walks each day near his home, this leading field theorist passes the house of a revered predecessor.
This house we're standing outside is the birthplace of James Clerk Maxwell. It's a reminder to me of the way field theory began in the 19th century.
As a pupil of Cotton School in Bristol, he excelled in mathematics. And then he became aware of a famous old boy of the school, the theoretical physicist Paul Dirac.
The name Paul Dirac appeared rather frequently in the school honours board at the back of the platform in the assembly hall. So I got curious about what Paul Dirac did. It very soon became evident when I was a physics undergraduate that I was not going to be an experimental physicist. I was terrible as an experimentalist. At King's College London, where I was an undergraduate, they'd introduced a theoretical option. So I gladly took that.
And it was as a theoretical physicist that Peter Higgs encountered theories by the Japanese-American physicist Yoshiro Nambu that seemed to point the way to understanding particle masses.
In the version of this type of theory which I formulated in 1964, which brought in fields like Maxwell's electromagnetism, fields of this type, in addition to giving mass to the fermions, the quanta of the electromagnetic type of field acquired mass too. This is what has been given the name the Higgs Mechanism, though it was actually written down a little earlier by Brout and Onglair in Brussels. And the generation of mass there is the same kind of thing as in Nambu's papers, but it is now working for particles of spin 1, which are the quanta of the electromagnetic type of field. They change from being particles which travel with the velocity of light to particles which travel with anything less than the velocity of light, and that's the massiveness.
Much of these new ideas centre on the rethinking of the nature of a vacuum.
When you look at the vacuum in a quantum theory of fields, it isn't exactly nothing. The vacuum state is the state of lowest possible energy. And again, as in the original classical idea, it's what you have left when you pump everything you can out of your system. Now, everything you can pump out is all the particles, but you don't necessarily get rid of everything. There can be residual fields which remain as a background in the vacuum. So the vacuum is no longer quite as empty as it used to be.
It's the interaction between this field, now known as the Higgs field, and particles that's at the centre of his thinking.
The relation to particles is that in these theories, this background could be deformable. It could be excited by interaction with other things. The excitations take the form classically of travelling waves and so on. But this is quantum mechanics, not classical mechanics. Every time you have travelling waves, the energy and momentum come in lumps.
And in the case of the Higgs field, these lumps are the Higgs bosons that the LHC is preparing to look for. What's intriguing about these Higgs bosons and their source field is that they appear to confer mass on particles.
The way that the background field generates mass is rather like the way in which when light passes through a transparent medium like glass or water, it gets slowed down. It no longer travels with the fundamental velocity of light, c. And that's the way to think of the generation of mass, because in a quantum field theory, all the other particles are also excitations of various kinds of fields, which you can describe by classical waves. Now, these waves travel through this background field, and the way they travel in terms of the relation between frequency and wavelength is altered by the background field, or may be altered. If they interact with the background field, it alters the so-called dispersion relation between frequency and wavelength. Now, when it comes to the particles, which are associated with those other fields, you take the frequency multiplied by Planck's constant, you take the inverse of the wavelength multiplied by Planck's constant. The one gives you the energy of a particle, the other gives you the momentum of a particle. And so altering the frequency wavelength relation of the waves propagating through the Higgs field alters the energy momentum relation for the particles, and therefore alters the mass.
The problem is explaining the considerable variation of mass between different particles.
In theories of this type, most of that variation is attributed to variation in the strength of the interaction of the particles with the Higgs field. Now, that's not really any explanation. It's simply saying there is a connection between the mass that the particle has and the extent to which it interacts with the Higgs field.
The LHC's detectors will look for hard evidence that it is these interactions with the Higgs field carried by Higgs bosons that are responsible for mass.
As a theoretician, of course, I find the mathematical structure of this kind of theory very satisfying. But on the other hand, if it's not verified experimentally, it's just a game. It has to be put to the test. At the present time, the interesting thing is that the electroweak theory of Glashow, Weinberg and Salam, which was the successful application of these ideas, has been rather thoroughly tested quantitatively for most of the relationships that are built into it in the course particularly of the running of LEP. Now, that has been done, it would be rather surprising to me if the underlying idea was not right.
If the Higgs boson exists, the LHC will have the power to detect That's assuming the theory is correct.
The theory fits the data in a crude way to about 10% accuracy if you just do what's almost a back-of-the-envelope calculation from the original equations. But then you have to do corrections to this first approximation. And into the corrections, the so-called one-loop corrections, come the masses of all the particles that are in the theory that maybe you haven't yet discovered. Now, during the running of LEP, they pinned down the masses of everything, I think, except the top quark. In 1995, Fermilab found the top quark and produced an approximate mass for it, and that enabled people to look at this correction formula and say, okay, what's left to fill the gap between theory and experiment? That's the Higgs boson contribution. Therefore, the Higgs boson mass should be in a certain range. In 1995, the prediction was a rather interesting one. It was that the most likely values were within reach of LEP, around about energy 95 or 90 or so JeV, and LEP went up beyond that. LEP went up to 114 and didn't find anything. And this was maybe a bit worrying because they were beginning to get to the tail of the statistical distribution. But in the last few months, new measurements reported by Fermilab have revised the mass of the top quark, and that favoured value, the most likely value for the Higgs boson mass, is about 117. Now that's tantalizingly close to what the people at LEP thought they might have found. Very puzzling for me to think of a situation where somebody could really rule out the existence of the Higgs boson, because there it is. There it is. The theory and the experiment are working very well together in all other respects. So where do you go from there?
Well, so we're also looking for the supersymmetry. So those are the two big things. Now, supersymmetry, though, also played, it started off about the same time as string theory, but turns out that the way they found that they could go from 26, requiring 26 dimensions in bosonic string theory down to fermionic string theory with 10 dimensions was through supersymmetry. It really requires unbroken supersymmetry, and they didn't find that. They would have found that at the LEP had it existed. So now they think the reason they didn't see it is because it's broken. If they would have seen it, if it would have been unbroken, they would have seen these particles, sparticles and whatnot that they call them. See, so here you see this is a broken symmetry, and they got to get to the energy where they can see these things instead of them being the same size and same shape. If it was supersymmetry, you'd be able to see them. But the idea that it's broken symmetry means that they're carrying much heavier momentum and so on. So it doubles the number of particles. It's a symmetry between bosons and fermions. In other words, in the equations, you can change it from one to the other. And it doesn't make any difference. It then, like I said, makes 26D string theory down to 10D superstring theory. And it provides for the standard model Higgs boson, and it must be broken. And so if they do find it, then the next question is, why is it, or how is it broken? So in the fermions, you take, like, say, an electron, and then you just add an S to electrons in front of it, so that electrons become selectrons. And with the bosons, a photon, for instance, becomes a photon when you drop the O in and put an I in on there. So that's what this is all about, if you can imagine. This huge construction project. Again, LHC, Large Hadron Collider. Hadrons being protons and neutrons, those big particles. And the whole idea is to collide those things together, spend these billions of dollars on this project to find that thing. Now, they tried to find it in Chicago at Fermilab and didn't. But this thing initially will be 7 times more powerful than what they had there in the Tevatron at Fermilab, and eventually 40 times more powerful. So they hope to be able to find these things. And again, see, here's a guy standing down here. It's just huge. It's unimaginable what it must be like to be building such a huge project. It would seem like it's bigger than the moon project was. But all this is because of the theories that began in the 70s, children of the 70s, the gauge theories that resulted in the standard model, the supersymmetry theory that they came up with to try to go beyond the standard model, and the string theories that became it was combined with supergravity, the 11D supergravity. But 20 years after that, in the early 90s, the gauge theory, of course, was still incomplete, didn't have any explanation for the masses. It didn't know about that Higgs. They had the theory of the Higgs, but didn't include gravity, and nowhere did Susie appear. So that seemed to be perplexing. And worst of all, this string theory that seemed to be everybody's great hope in the mid 80s turned out to have 5 theories. This type 1, type 2A and B, and then heterotics. That those combine the 26 and the 10-dimensional one, the bosons and the fermions together. So, and then the 11D supergravity, which got everybody all excited for a while, was going nowhere, and so on. So, then in 1995, there was this breakthrough with Edwin